Okay, so recently I've been messing around with water shaders a bunch in Unity, specifically like an ocean shader in the HDRP shader graph. Um, just trying to implement things like foam, refraction, all that good stuff. You can see the shader here. It's kind of what I want to like show off. Um, it's got the wave crest foam, edge foam. You have some depth refraction and some blurring effects as the depth increases. I'm using Unity's built-in tessellation, although it's not really necessary with these planes, with these water planes. Um, but if they were lower res, this would be a lot more apparent, I guess, or a lot more useful. Yeah. And yeah, I have everything split up into different tiles in the ocean, or different planes, and everything's tiling together using, the world position of the vertices to sample textures and stuff. Um, and this is just the basic scene I was using to like test everything. It's just some terrain, a couple objects. But yeah, I'll go through some of the steps, or showcase the steps I went through to make this. So I guess before you start doing anything, we can change some of the settings in this graph inspector. So our material will obviously be lit. Material type, we want it to be standard. Surface type, we'll set it to transparent so we can access things like the depth buffer. Scene color. Depth test is fine. We want it double-sided, wherever that option is. That might be in the material options. You can enable tessellation. It'll add this tessellation parameter right here, or you can just use the normal vertex position offset if you'd like. And then, and then if you want so I was using screen space reflections in my shader. You could just check that, enable it right here, receive screen space reflection, transparent. If you do want the screen space reflections, you will have to enable them in your project settings on your camera, I believe. And then I was using Gerstner wave generation to take care of the height displacement and everything, tiled together with one sine wave, or combined together with a sine wave. And to do that, I used this. I was referencing this article on the developer, on this like developer NVIDIA article, NVIDIA. It just goes over different equations for generating sine waves or different types of waves, such as sine waves. You scroll down, I used this Gerstner wave function. You can see, so for the x, and then this y would actually be z in Unity. We have these would be the equations for the offsets, and then this third equation is for the height. This Q parameter here is steepness. A would be amplitude. This capital D that you see here and here, this is just a vector 2 direction. And then W right here, that would be frequency, dotted with the X and Z vertice positions. And then this phi is just like a speed, or a variable that we're multiplying with time to change our time scale. And so yeah, we can implement these first, I suppose. So back in Unity, in our shader graph, we'll get a position node, and we will split this out into the X and Z components. And this will basically be our world space UVs to tile everything together. And then we'll also go ahead and get a time node. Put that right there. And so according to this article, so we'll need a steepness, amplitude, vector 2 direction, frequency, and speed variables. So we can go ahead and create these. We have amplitude, frequency, steepness, speed, and then create a vector 2 and call it direction. Okay. And so I'm actually going to group these as well and just call them, like, I don't know, UVs and time, I guess. So the first thing we can do according to this equation, multiply steepness by our amplitude. So grab our amplitude, steepness, just simple multiply, set these together. Next we can grab our direction. We'll want to normalize this so that it always has a length of 1. You don't have to normalize this, but of course if you don't, then it'll interfere with the frequency when we multiply them together. So we can multiply these together. We will also, well, we also need to split this out after we normalize it because we'll need to access the X and Z components separately. That there. And then the last thing we'll do is multiply our time with our speed parameter. That. And let me go ahead and set just some default parameters. So just 1 for everything, I guess it's fine for now. Maybe frequency. We'll put it 0.5, speed 0.5, and for direction we'll go the X value of 1. Okay. So the first thing we want to do is multiply, or sorry, not multiply, take the dot product between our vector 2 world positions and our direction multiplied with frequency. Dot product. And we can always sort of, I guess, debug by just plugging everything into the base color if you want to see what it's doing. This will be creating, so we're not, oh right, okay, so you can also see how this is following the camera sort of. We need to change this position to absolute world position, so it's not influenced by the camera position at all. Now I can see that's fixed. And what this is doing is it's just creating a mask going in, like, increasing, like just continuously increasing in values from, or based on our direction. So if we change our direction, whoops, change our Y direction, you can see, how that's working. If you wanted to debug it even a little further, you could, maybe put this in a fraction node and then output it. And it's very clear, how how we can just take the sine of this to generate waves. This would be, the super simple sine waves if we were to simply take the sine of our dot product. But we're not going to do that. We're going to do a little bit more, some more complicated stuff to it to get our Gerstner wave generation. So next, what we want to do is add time to this dot product. So that everything is increasing. So we have like, continuous movement for our waves. Then we'll take the cosine of that. Here. And here we can multiply these with multiply this. So if we look at we just took the cosine of our frequency and direction, dotted with our vertice positions, added to time, and then we can multiply that by the x and z direction components, and then multiply that with our steepness and amplitude. So we split out our directions right here. We'll multiply these. So this will be the x. And then copy that and multiply actually, so we'll use g. This is just a vector too. Multiply those together, and then we can multiply that by our steepness and frequency, steepness and amplitude. Might actually be cleaner if we do that first, so actually multiply that right there, and then multiply it with our cosine. And so this would be our x and z offset components. And all we need to do now is calculate the height, which is very simple. It's just the sine instead of the cosine of that, and then we multiply it by our amplitude. So we grab this, take the sine of it, and then we multiply that, with our amplitude over here. And then we can feed these all into a vector 3, like this, and then put that into either our position or our tessellation displacement. I'll set a factor of 2 for that for now. Save that. Now you can see we have waves made on the shaded wireframe because we're not updating our normals yet. So yeah, you can see we have some nice peaks. If we increase the steepness, you can see how that shifting these vertices near the peaks towards the center. Amplitude, obviously, since these are being multiplied together, you're gonna have to tweak these depending on frequency, obviously, and speed, all working as intended. Turn the amplitude down for now. You will notice this culling around the edges of our screen. We can just turn up this max displacement to something like 1 to get rid of that effect. Probably don't even need 1, it might be overkill. But I'll just leave it on 1. We have a triangle size as well, that just is controlling the the minimum size of the triangle, basically. And in the example shader, I had a sine wave added to this to break it up, make it. Oh, actually, one thing I also forgot. So you can see, if you look at our little gizmo in the top right, you can see that the positive z and x directions are well, basically our waves are going in the negative z and x directions, even though we have the direction set to a positive x and a positive y, or z in this case. To fix that, we can just negate this after we normalize it. And now it'll just make this clearer and help out with a few more calculations we'll be doing down the line. It'll just make things cleaner and easier to work with. Save that. And now we have our waves going in the proper direction. So I'll go ahead now and add the additional sine wave that we can combine with this Gerstner wave to break it up. I gave it its own frequency, speed, and direction. So we can just duplicate these values, rename them. I'll rename this secondary frequency, secondary speed, and secondary direction. I'll also add categories for everything. So I can call this category secondary wave parameters, and I will want one more category called primary wave parameters. And I'll put the first 5 things we made into the primary wave, and then these are the secondary. Drag that up. Now we can just basically reuse or copy these, what is this, 5 nodes right here. We don't actually need the split node, so let's duplicate that. Drag that down a little bit. And then we'll obviously replace these variables with the ones we just made. Speed will go in there, and then let's see. Okay. And then we'll again do the same thing. We'll take the dot product, add our time to it. Oops. So dot product with our wave direction and frequency. And then we will add time. And then, of course, take the sine of that to get the height. We only need the height offset for these waves. And then we'll just add these together with our Gerstner wave height. So let me move this over a little bit. Add node. Add that together, and then multiply it by our amplitude. Go ahead and save that. Look at our scene. You can see how the sine waves are breaking up the Gerstner waves a little bit. You can see that they're following this, since the direction is just going straight along the x in this direction. Usually, obviously, you don't want the frequencies to match, the frequency and speed to match with your primary waves. So I can put this on like 0.3, put this one on 0.6 maybe. Speed 0.4, speed on this one 0.2. I like just cutting it in half, but you can mess around with those parameters. And then we can set the wave direction, I don't know, 0.3 maybe. So yeah, that'll take care of all the height displacement that we need. So we can group these nodes we just made into a group, call it height. So now we can drag that around and keep everything organized. We can calculate our normals now. I do also have, generally when you do ocean and water shaders, you want two normal maps sort of scrolling together. Combine them and have them offset in opposite directions to simulate like a shiny water effect when you have a very high smoothness parameter. I have two. These are just two normal maps, water normal maps I made in Substance Designer. They're not great, but they'll work. They could definitely be better. And then I also have a foam texture. We'll use that later, but basically I only need 3 textures right here. This foam texture, water normal, and then a secondary water normal. And make sure these are, your normal maps are tagged as normal maps in the texture type. So I can go ahead and add parameters for those. Those will be texture 2Ds. I'll call it just normal 0, 1 and like normal 0, 2 maybe. And then in addition to these, we'll need parameters for the ripple strength, the ripple tiling, and is that it? Let's see. Oh, and our ripple speed. Okay. I'll give these defaults for now. Just 1.3 on the speed. So get our normal texture 2Ds, and we'll sample those with a sample texture 2D node. We'll set the type to normal, space on tangent, and do the same thing for this one. Okay. So here. And then we'll also take our normal tile, or our ripple tiling, excuse me, and our ripple speed. And again, we'll use the world position vertices in place of our UVs to sample this. So we'll take that, just multiply it by our tiling, and then we can, we do need to offset these as well with time, because we want them to be scrolling back and forth. So we'll take time, multiply it with our ripple speed, and then since we want these to be going in opposite directions, we'll add the time to 1 of our add time with the UVs for one of our samples and subtract time from the other one, and then put those in our UVs. So if we preview this, or well, we don't have, grab the default textures or the default normals. We will also need to tag these 2 variables as normal maps as well, for defaults anyway. Now if we look at this, we can see they're tiling together. And then to combine them together, Unity has a normal combine, or normal blend, I think it's called. Yeah. Not that blend. Normal blend. Okay. Plug those in. Just leave it on default. And you can see how our normals are sort of, well, yeah, you can see how they're blended together, flowing in opposite directions. We'll put this into a normal strength node. What? No. use that node. String normal strength. Okay. Our normal strength, get our ripple strength parameter, just plug that in. I'm actually going to set this to 0.2 as a default. Okay. And then we'll also want to recalculate the normals from our wave generation, our height map. So if we take this y parameter after we multiply it with our amplitude, we can plug that into a normal from height. Normal from height node, I just leave the strength at 1 by default. Over here. And then we'll again, we will blend these normals together. And that actually takes care of everything we need for the normals. So we can go ahead and group that. Call it normals. Drag this group to an appropriate spot. And then output that into our normal slot. Save. And now you can see we have normals. Beautiful. Yeah. Where are my ripple normals? Oh, they're probably not assigned. So water normal 1, water normal 2. Turn on the tiling, I suppose. Two. See, we have the strength set up. Speed is definitely too fast. And yeah, so let me go ahead and crank up our smoothness parameter to something like 0.9. It's just to make it look more like water for now. Yeah, you'll see that we get this glistening water effect with our normals tiled together, or blended together like this, and then flowing in opposite directions. Okay, the next thing I want to tackle is a foam mask. We'll do both the edge foam and the wave crest. I will actually make a category first called normal parameters and put all of the variables we made in here, or the parameters. Okay. So for edge foam, we'll need to access our depth buffer. And to do that, we need a scene depth node. We'll set the sampling space to I. And we'll also need a screen position node set to raw. And we'll split that out and grab the alpha component. This alpha component contains, it's basically, I guess, the pixel depth of every pixel on the objects we're rendering, or with the shader that the shader is applied to. So it'd be the distance of, each pixel on this plane from the camera, essentially. And then the scene depth, it will return the pixel depth of all the, or the depth buffer, which contains the pixel depth of all the, I guess, opaque objects that have been rendered previously, like our terrain, this cube, and this sphere. And when we subtract the currently rendering geometry with our material from the you know, the depth buffer contained, or the depth buffer that we got from our opaque materials, we'll get a basically a mask that is 0 where they're, or black where they're basically the same, and then it'll gradually increase to white as we have, you know, a greater offset, a greater delta between the two. And so all we need to do is just scene depth, subtract our alpha, and that's basically all we need. And then we can obviously, you know, multiply this by decimal to, you know, flatten the offset, or the slope, I guess, at which it the slope at which the depth is increasing. Multiply that by like 0.2 or something. And we can go ahead and view that output. So just take that. We'll saturate it first because we're going to have values way above 1. Put in our base color. Oh, and so we're going to have to make sure our material is set to, since I created this before I changed some of the shader parameters, got to set this to transparent surface type. And now we can see our edge mask, depth edge mask, basically. I will also turn on double-sided in the material, because we will need it later. Mirror the normals. And you will see this, so this weird culling effect when we get, you know, down by the down lower by the water. To fix that, you can just turn on depth rate up here in the surface options, and that should fix that issue. Okay. Anyways, onto our foam. So we'll start by adding a few parameters. I'll add a foam fall off, add a foam width. Let's see. I'll add something called foam removal and foam bands. Okay. Oh, and we will need that foam texture as well. The foam texture that we imported. So I'll go ahead and sample that to start with. We'll actually turn on the tiling and offset because we're not going to be offsetting it with time or anything, so we can just use the built-in Unity option for that. So the idea behind this is that we take the cosine of the depth value as it increases, and then offset that by time, or offset the depth and by time, and then take the cosine of that. And that'll give us like a radial, some like radial waves oscillating out from the from like our terrain, the edge of our terrain. So if we want to visualize the that banding effect, we can just take our time variable, add it to the depth, and then we'll just take the cosine of that, and we can output that in our base color. And so yeah, we go back to our scene, we can see how the so these are actually flowing the wrong way. But yeah, we have this effect where the bands of these bands are, flowing, in this case, towards our terrain, but if we just reverse that, they'd be flowing out. So if we just, instead of adding time, we will just subtract it from our depth, and that'll make it oscillate in the proper direction, as we can see here. Okay. But I'll delete this for now. So the first thing we'll do is we'll take our depth right here, the scene depth minus the current, rendering object pixel depth, and we'll multiply that by our fall off. Then we'll subtract our foam width from that, and so this will just bring values near the edges of the terrain below 0, and that'll, it'll bring basically our 0 point out further, and then we'll just clamp those. So, and then we can multiply this by our foam removal variable. This is just like additional fall off after we do some calculations to this and this separately. Okay, so then we can take our foam fall off and multiply that with our foam bands here. And then here is where we can take our time variable and subtract this banding effect, or the foam bands. And then from here, we'll take the cosine. Right here, so this again is our foam width. We're just basically increasing the range, the values that are below 0, so that when we clamp that using a saturate node, the saturate node clamps all the values in the 0 to 1 range. You can multiply that with this cosine, and then we'll have basically so it'll be black on the edge, and we'll just invert it with a 1 minus node to flip everything. So we go 1 minus. So now our edge will always be white. And then we can multiply that with our foam texture. I'm just using the R channel. So now if we take this multiplication and we subtract the foam removal, the value that we multiplied by our foam removal, and then we can go ahead and view this in our, well, we should probably saturate it first, because we will have values outside of the 0 to 1 range. Oh, and some of these defaults are probably, some of these default values are probably not set up properly. So I'll just put everything on 1 as a default. Except for the foam bands, we can put this at like 5, maybe. Texture. So, fall of 1, 1, 1, and the bands at like 5. So yeah, now you can see this banding effect that we have, where the edges are staying white, and it's gradually spilling out. Change the fall off to 2. The width, it's just that, you know, obviously the edge foam width that never changes, will always be at least 1 according to this. Change this foam removal, which will increase the width of the banding. Can also change the number of bands right here. And then, of course, we apply our foam texture. It's a little hard to tell, but it just breaks up the banding effect, essentially. And then this would obviously be like a mask for our that we blend or we lerp between a watercolor and a foam color. But first, I will set up the wave crest foam and blend the two foams together, and then we'll use that as the color mask. So to do that, or actually let me create a category for these. Call it edge foam parameters. Edit there. Save that. Oh yeah, I should, normally I increase the tiling on the foam texture, which will, you know, obviously break it up quite a bit if you want. I will be using the same foam texture to sample, or the same foam texture for the edge foam and the wave crest. You could just sample it again with if you know have a variable to change the tiling, because it looks pretty good like with a high tiling value on the edges, but it's very noticeable on the wave crest, so you might want to split that up and just sample the texture twice, so you can have a low tiling for the wave crest and then a high tiling for the edge foam. But I'll leave it at 2 for now. I like 2. I just use 2 for both of them in the tiling. And we'll also, so for the wave crest, we'll add a few variables. First, we want the, so we'll call this crest fall off, I suppose. Whoops. We'll add a, let's see, crest size. Can add a crest offset, and then we'll add a variable called extra dispersion. Like that. And so first we'll take our crest offset, and then we'll grab we'll grab this output right here, which is, you know, just the dot product of our, these are our Gerstner waves, the dot product of our Gerstner waves with the direction. We'll grab the output after we add time to it, so it's again moving. We want our wave crest to move with our waves. So we'll add that with our offset. If we want an offset to reposition, you know, where the crest sits on the wave, on top of the wave. So we'll add that, and then we will mod it with a constant. We'll mod it with tau, and the reason we do this is because when we define the function that controls the fall off of the wave crest, we want a very sharp fall off right at the front of the wave, and then we want a very gradual fall off on the back of the wave. If that makes sense. So, we want it to sort of be like misty and not misty, but we want the breakup to be very slow and apparent on the back of the wave. And to do that, we have this equation right here. So if you take a look here, we have this vertical line is where x is equal to 2 pi, and 2 pi is tau. And we always want this interval to tile together, so it starts at 0, very gradually increases to 1, and then has a very sharp drop off back to 0. And since we're modding our x value by tau, then this value will just loop indefinitely. So we'll always have this wave pattern. And the equation is this one right here. We just take the cosine of, so if I sort of recreate it, so if we have the cosine of x, this is just a normal cosine wave. If we raise x to some value, say 3, we can see how the fall off is getting, or how the waves are getting very, contracting, they're shrinking, they're compressing, I suppose you'd say. I'll store that as a variable for now, like z. So we can control that. And then, in order to, anchor this peak right here on tau, or on 2 pi, we want this to always be anchored onto that position. Then we'll need to obviously multiply x by some value. So for example, z is 3. We'll need a value around 0.025. And so that'll create that continuous effect when we mod the x value by 2 pi. But obviously we don't want to just guess and input this manually. So if we set this as another parameter like w, or actually we won't use a slider for these, we'll want to calculate them we'll want to calculate our this variable that we have to multiply by based on our z value, which in this case this is z value. This will be our crest fall off variable. So we have the crest fall off. Could actually write this out if we want. Or actually, I don't even know if you can store variables like that in Desmos. I won't worry about it. But z is equal to our crest fall off. Then we need to calculate w. So w is equal to, again, you can see it up here. W is basically a in this situation. W would be equal to pi times, let's say, again, we'll store this as a variable for now. Pi times q over pi raised to the z. So we have this slope right here. And then if we want to calculate q, which in this case is equivalent to n, q is equal to 1 over 2 raised to the power of, again, we're using this will be our crest fall off variable, which is z, so z minus 1, and then that will anchor our wave in the 0 to 2 pi range, where our where the wave intersects 1 is at 0 and 2 pi, and y. Y is equal to 1 where x is 0 and 2 pi. And then obviously we want to shift this in the 0 to 1 range as well as flip it around. So come up to our cosine of w times x raised to the, again, this would be our crest fall, z. All we have to do is multiply it by 0.5, and then add 0.5, and now that's shifted into the 0 to 1 range. Y is between 0 and 1, inclusive. And then we can just invert that by subtracting, or doing a 1 minus operation. And then if we sample the foam texture using a equation like this, then you can see how when we're subtracting values on this gradual slope, we'll get a very slow fall off versus the front. It'll be a very sort of hard edge, but not, I didn't want to direct, just linear increase that then has a very sharp edge that falls to 0 because that wouldn't look natural. So we have to do something like this. You can see how I increase and decrease this, it just cranks up those fall off values. So we'll implement this into Unity, or into the shader graph. So we have the crest fall off. I guess the first thing we can do is raise our x value to a power of the crest fall off. One thing to note is that you get a warning doing this operation, because when our scene time is basically 0, we are, this dot product can go, it will go into the negatives. We'll get negative values depending on which way our direction's going, based on our vertex positions, because position of these is, again, x 70, z is 70, and our direction vector is 1 and 1, which, remember, we're negating that, so it's actually -1 and -1, so we'll get, like a dot product of -70 and -70. Then when time is 0, we're adding to that, so it's still negative. The values are still, or the dot product would be -70, so we're getting, and then we're adding time to that. But if time is 0 because the game just started, this will remain -70. Again, we're adding an offset, but this offset is less than 70, it'll still be negative. And so we get an error if we're putting that negative into this power node. To fix that, we can just clamp this value to the 0 to tau range. And that'll fix that error when we get it. I am recording this in the future. Thinking back on it, I realized we should just, instead of clamping the values after using the built-in mod function, we should just create a custom function where we do the mod operation, and then we test whether or not we get a negative value out of it, and then basically output that added to our mod value, just so it's always it always returns positive. Because I realized when you load up the scene and the time is 0, then the wave crests will basically it won't be applied properly until the time value is equivalent to the x and z values of these planes that have the water applied. So when time hits 70 or something, then we'll finally actually see the wave crest working properly with the parameters. But if we just do it like this, then it doesn't matter what our time value is. It'll output properly, and it'll always be positive, so we can take the power of it and yada yada yada. So the next thing we're going to do is calculate this n value right here, which is then used to calculate this a value, which is the factor that we're multiplying our waves by. So in order to calculate n is 1 over 2 raised to the b minus 1. So we will get a divide node, set that to 1. We'll need a power node. We'll also need, we'll set this to 2, then we'll need a subtract. And so we'll take our b value, or our crest fall off, subtract 1, raise that, or take 2 and raise it to that power, and then we will divide all that by 1. And then we'll calculate the a, which we just need the pi constant times n over pi raised to the b. So if we get a constant, pi, since this is our n value, we'll multiply these together. And then we'll also take this constant power and raise it to the crest fall off. Like this. And then we just divide these, or divide our power by the multiplication. So now that we have this set up, we just multiply them together again. Again, this is our a value, basically just multiplying our x component by a. That was all the calculation for the a component. It is a little expensive to do this, so it is, you can just use a, just a hard-coded parameter like 0.025 like I did if the offset was 3. Or you could calculate it like this, but we are using 2 power operations and 2 divide operations. So it isn't exactly cheap to do, unfortunately. But yeah, we multiply those, take the cosine. We want to take the cosine, not sine, because cosine will be 1 when x is 0. Now, of course, we do the 1 minus, first we multiply it by 0.5, and then add 0.5 to shift it into the 0 to 1 range. And then we can flip it, or invert it using 1 minus. Okay. So that's our basic wave. Set defaults. No, crest fall off, I'll set that to 2. I have not implemented size or dispersion, but we can go ahead and just take a look at this, put it in the saturate node, and output it in our base color, and just see what it looks like. Right now we're only accounting for the Gerstner waves, but it's fairly easy to account for the sine waves. We blend it in with it. So you can see where's my material? So you can see the sort of wave we have. We have a very steep fall off right here, and then a very gradual one towards the back. We just increase that fall off. You can see how that's changing. We have an offset if we want to reposition the wave, and we'll be subtracting our foam mask from these grayscale values. So we'll get, white, so we're subtracting the mask, we'll get white values, and the foam mask where it's black, and then where there's white, we'll get nothing, or we'll, have the normal watercolor. So to add in the secondary waves, we just take this addition of the two right here. So our final height before we multiply the amplitude. And I will take that, add our crest size to it. I'll saturate this because, again, we'll have this value is already in the -2 to 2 range, since we're just adding two sine waves together. So we'll add the crest size, then we'll saturate it. Do a 1 minus, which we'll need in a second, as well as multiply this by multiply this by our extra dispersion variable. And we're multiplying the extra dispersion in first, so that we're only dispersing. If we take this, extra dispersion negative, we still only want it to affect like or make it positive. We only want it to affect the waves. Like we don't want it to affect the troughs. So we just need to make sure we're multiplying that together before we add it in. So we can take our extra dispersion now, add it together with the cosine wave, and then we'll take this and just add it together. This is like our wave size mask. And then if we, similar to how we did for the edge foam, we just took our foam texture and subtracted the mask from it. We'll do the same thing. Take the foam texture, subtract our mask, and then we'll saturate it. Take a look. Why is this dispersion? Dispersion. There we go. Okay, and now we can see how our waves are appearing, where they should on the peaks, the highest points of our water. We have a fall off, an offset, which will offset it within our this sort of like size mask. We can change the size. We can change the extra dispersion. So you can see it's just dispersing it or just adding. If you really crank it up, you'll get this effect, but yeah. And then, so then what we want to do is we want to combine our crest and edge foam together. So we have the two subtract nodes. All we're going to do is just take the max of both of those. So we get the maximum. Here, I'll introduce another variable called the, let's call it foam edge hardness. I don't need to just call it edge hardness. Well, that's fine. Actually, no, it's not fine. It's too long. Edge hardness. Give this a default value of say 10, perhaps. And then before we saturate, we'll just multiply our foam mask and everything by this edge hardness value. Saturate it. Save. And that is our wave crest foam and edge foam complete. The mask anyway. Just add the color later. So you can see how our edge hardness is affecting the wave. Obviously, we go negative, that'll invert everything. Really crank it up to get a very sharp edge if we want, like 200. This is affecting both the edge foam and the wave foam. I'll leave it on 10 though. Maybe tweak our extra dispersion touch. Change the offset a little bit. We can change the size if we'd like. And of course, it's affected by our wave direction, everything. But yeah. Now we can use this mask as a color mask. So first, I will group everything. That. Just call it foam. May also group this. Call it depth. Just a simple depth calculation. What we can do now as well is, since we have our foam mask complete, we can now add a smoothness parameter. Or we can now calculate our smoothness. All we want is just the water to be smooth and the foam. Even though it doesn't really make sense, we do want the foam to be smooth. I didn't add like a separate normal mask for the foam or anything, normal texture. But you could. You just have to, blend it in the correct place in our normal map. But I will add a variable, call it smoothness. This is just our overall material smoothness. All we need to do is just take the smoothness. I believe we do a 1 minus. And then we just multiply it with our foam. Or sorry, we put the foam mask into the 1 minus and then multiply by smoothness. Because the smoothness value of 0 is very rough and diffuse, and our foam mask is white, so if we just invert it, it'll become black, and then we multiply by the smoothness to affect the overall water smoothness. Group this as smoothness. Set the default 2.9. And we can see the effect that's having. So now we don't have our specular highlights clearly visible on the foam anymore. Can of course change the smoothness parameter, but yeah. So let me make a category for these. Crest foam parameters. I won't put the smoothness in there, but I will put all the other stuff we made. You will have to be aware that the edge hardness is applied for both the edge foam and the crest foam. I just have it in this category. It's up to you where you put that though. I'll go ahead and do the albit or the base color. So normally when people do water color, they take the view direction, which is the direction of every pixel towards the camera, and then they dot that with the normal direction of the water. Use a dot product to get a mask, just to create variations in the water between, right below you it'll be one color, at the sort of on the face of the wave that'll kind of blend to that color, and then obviously, well, dot product works. Why am I explaining this? But to do that, we'll use this normal blend right here, and first we need to transform that to world space. So get a transform node, It's in tangent currently, so transform it to world. We'll use direction because this is our normals, and normals are directions. And then we'll get our view direction, which is in world space, which is fine. And we will just take the dot product of these together. And as you can see, we have that Fresnel effect. I believe Unity does have a Fresnel node, yeah, which we could use. You would plug in these transform normals right here. And then we can change the power. But this works fine. Just doing it like this, I just square it once to give it a sharper offset, sharper fall off. And then we can introduce two color parameters. Color 01 and color 2. And we'll just lerp between these with a lerp node using our Fresnel mask. Can't swizzle these out as well to vector 3s. I don't know if this is more efficient or not, but you don't need the W channel in our case. So we'll just lerp these together. So that'll be like our wave base color. We will get another lerp node to lerp in our foam mask. Oops. So we have our foam mask here. We'll take a lerp. And then, so we'll also need a foam color. Go ahead and put that in the, or here, let me set it default white. We'll put that in the foam parameters. I will swizzle it again, even though I don't know if it's efficient or not, or inefficient to do that, but I'm going to do it for now. We'll just lerp those. Wherever the lerp node is, I believe 1, it'll fully use the B input, and where it's 0, it'll use the A input. And then we can put this into our base color. Group this, I'll call this view direction base color. And we can just group these as into our base color combine or something. That. So color 1, I usually go for like a greenish teal color. The second, I'll go for like a dark blue. This. Probably also turn down my normal strength, or the ripple strength. This. But yeah, that works. And then we have the foam color. Set this to like an off-white. That. And yeah, that is mostly the base color. We will. So we do want to add the refraction in, like the depth and the depth refraction and all that. So we're going to need to sample our scene depth, and that'll be blended in with our base color or our scene color. So we'll need to sample the scene depth again and the scene color, and we'll blend that in with our base color. So to do that, we will first start with a screen position node. You can leave that at default, and if we just straight up sample a scene color, we'll use the HD render pipeline scene color. Check the exposure, or else everything will be extremely bright. Now we can just take a look at our scene color, or see what these nodes are returning, which is just the base color buffer, render buffer. So yeah, you can see it's just returning the existing scene color at every pixel position. And so we'll offset these. We'll basically offset the screen coordinates using our normal map, and that way we can mimic refraction. So if we take our normals, we don't want the wave normals, we just want the ripple normals after our normal strength is applied to them. So take that, split it out. We will also split our screen position. And then so we have the X and the Y normal channels. This is what we need, the R and G. And we should introduce another parameter. We'll call this refraction strength. Default it to like 0.5. So first we will multiply the normals, the R and G channels, by our refraction strength. So multiply it by the G channel, like so. And then if we just add this back into our screen position in the respective channels, reconstruct the vector for our screen sampling positions, and then plug that into the scene color node. And then we can see we have the refraction, basically, the refraction effect. Turn down the strength a bit. You might be able to notice one of the issues with the refraction, doing the refraction this way. First off, the edges of our screen might, we might see like behind, I guess, our scene, like maybe our, I don't know exactly how this is working, but basically just a default white texture, it looks like, where since the refraction normals are not anchored onto the edges of our screen. And you will also see that even though this cube, for instance, is out of the water, it's still refracting behind it. Same with the terrain here, the edge, even though it's well out of the water, we're seeing refraction as if it was in the water. So first, to fix this edge on the screen, what we can do is go to desmos, and so if we have, this is our screen X and screen Y, or pretend with that its X value is like the screen X, and we want to clamp that to the 0 to 1 range, or we basically want where the values are close to 0, we want it to be 0, where it's 0, we want it to shoot up and form a sort of plateau, and then shoot back down when it hits 1. And then multiply our normals with that. So if we square this, you can see we have, basically the slope we need. If we subtract 1 to offset it, now it's centered, 1 unit over. And if we just multiply it by 2 to, squeeze it closer together, change the fall off, then we have the basic. We have it in this 0 to 1 box range. All we have to do is flip that around by subtracting 1. So now we have, the fall off we need. Now we just need to basically increase this, make this a lot sharper towards the edges. So all we need to do for that is just multiply it or raise it to some power like 10, and we'll get this very plateau-ish type mask that we can use to multiply. If our screen coordinates are a variable, then we can multiply our normals with this to anchor them on the edges of our scene graph. To do that, we'll first take all we need is the RNG. First we'll multiply them by 2. Multiply by 2, then we can subtract 1 to shift it over. We'll square that. So yeah, you can see that we have the parabola shape that we want. And then basically all we need to do is just raise that to a very high power, like say 10, and you can see how this is changing that fall off, changing the mask. Now obviously we'll invert this with a 1 minus at the end. We'll set this to like 15 maybe. And then we just do a 1 minus. Like this. And then we can just copy that verbatim. Don't need to change anything except use our screen Y position instead. See, we have the black borders at the very edge, top. Oh, Command Z. You think about it when you hit Command Z. And so yeah, so now we can just multiply our normals with these 2 masks here. So move all this over. Take our X, multiply it with our screen X mask, and we'll take our Y, multiply it with our Y normals, and we'll feed that into the multiplies with our refraction strength, and then everything should be good to go. And then you can see it's anchored to the edge of the screen on the left. There's no gaps or anything. Top, bottom, left. You can still see gaps if you really crank up this refraction strength, like right here. It's not very noticeable when it's this high. So yeah, I don't know. It's not 100% foolproof, but it works well enough for me, I think. And then the next thing we'll need to do is get rid of this, this refraction out of the water for objects that are out, not in the water. So what we're going to do is use we're also going to refract our depth. We're going to sample depth again using the same refraction coordinates. and we'll use that to lerp between this scene color and, you know, the existing water foam base color. We can sample our scene depth, or scene depth. Again, set that to I space. We'll do the same subtraction, so set that as our B, and then grab our alpha value from the raw screen position, and plug that into our A. Sorry, these need to be reversed, so this will go in our B. And yeah, so we're subtracting the existing scene depth, which is behind the water planes. You know, it's at a greater distance. We subtract that from the current rendering geometry, which is the depth of the current rendering geometry, which is its alpha value. So we have that delta, and we can test whether it's negative with a comparison. If it's less than 0, then we will multiply it by -2. We'll get a branch. So if that is true, if it is less, then we'll multiply by -2, or else we'll just return the value. And so we can use this mask to blend between the refraction and the scene color, and it'll remove the refraction behind objects that are out of the water. First thing I will do, so I also do need to add a few more parameters now to control, you know, that opacity fall off and that blending with the water edge. So I'll add a depth strength. I'll add a water opacity, add a water edge opacity, and I think that's all I need. I'll add them as we go if I need more, but for now, first thing I'll do is multiply our depth strength with this output. We'll saturate this after we do that. Next, we'll take our water edge opacity. We'll subtract 1 minus it. Subtract it from 1. Multiply that with our saturate node. And then we'll also add the variable back into it, like so. And we will want to set the opacity variables to sliders, clamp to the 0 to 1 range. We don't want those to go above or below those values. Depth strength we can set to 0.2 as a default. And so now if we take this opacity mask, and before we blend in our foam, we want to blend in our scene color, which is, you know, basically our watercolor too. So we'll take this, put it in a lerp mode. And then we'll take our watercolor, put it in the B slot, take our scene color, put it in the A, then this group right here, and then put this output into our lerp with the place our watercolor with the new combined color. Then we can output this to our base color, save. And now you can see that we have the yeah, we can see we have like a fall off where we can see the terrain. Change so we have oh, I didn't implement the water opacity yet. To do that, we would just multiply everything at the end here. I'll do that real quick. Multiply that by the water opacity, use that as our mask for the lerp. Save. Okay, usually you probably just want water opacity at 1. I'll leave mine at 1. We have the edge opacity, which controls the edge. At like 0.8 maybe. And of course we have our depth strength. So turn that down. Up. So yeah, that is our refraction working. You can see that there is none of that depth effect occurring along this edge because we're just lerping with the normal watercolor instead of the scene color. There is, if we do have depth that's basically we have 2 objects sort of like overlapping fairly close to each other, or actually not even close to each other, just 2 objects are overlapping like this, then the only issue with handling the refraction in a mask like this is that you will again see this, we can see the normal watercolor where we should be seeing the underwater terrain. I don't know, there probably is a better way to avoid this. It's probably something I'll work on, like maybe blending with the normal, like multiplying by the normal scene depth right here. But this method works fairly well. Granted, you don't have like really high refraction strength. But yeah, we can see, like, if we're behind this cube, we'll see a little bit of that effect occurring right here along the edge of the cube, where we're getting watercolor instead of the terrain color. But for the most part, it works pretty well. The last thing we can do is add an effect so that our terrain will blur as the depth increases. And we can also make sure that we can actually see through the water when we're underneath it, instead of just up at the edge, as you can see. So to do that, there's a pretty handy node called go to utility logic. We have this is front face node right here, and obviously it'll return true if the face is, obviously a front face, or it's the normal direction it should be facing, and then these are back faces, so it'll return false. And obviously that's either a 1 or a 0, so if we have a mask like that, we will need a custom node here, because we want to convert this to a float, but in ShaderGraph there's no like Boolean to float conversion or anything, I don't think. Yeah, they don't let you do it or with like a node, so we just need a custom function. We need an input, which is a Boolean, and an output, which is a float. I'll just name it in and out. Set this to string. Call it bool to float. And all we need to do is just set our output equal to our input. Like that. Very simple. Then just put our front face into that. And now we have a black and white mask that will return. Will be, so if we're at the water level here, this will be black. Then above the water will be white. So we can use that to control the opacity. So if we take that, before we multiply with our water opacity, we take this, multiply these together, and then we'll set that multiply back out, and then rewire it like that. Save that. And as you can see, when we're underneath the water, we can very clearly see through, see to the, background, whatever's behind it. And then when we're above, it works as normal. When we're like in between, the water levels, the camera's in between, under and above the water, it'll work perfectly fine as well. So yeah, that takes care of the underwater, and then last thing we want is that depth blur effect. And that's also a very simple fix. All we basically need to do is just take this subtraction here and plug it into the LOD sampling part of our scene color. Save it. So now if we look at our terrain, we can see that we're getting this blurring effect as it gets deeper. You will notice if I turn my water opacity to 0, we have this black mask that's occurring, or this dark area. This is just because we're not clamping the LOD level that we're sampling, so it's sampling LODs that don't exist, or I guess LODs past LOD 6, I think. I think it usually has 6 LODs max. Not 100% sure on that, but yeah. So we can just take this, clamp it from 0 to 6. We might also, so even though this is right near the surface, it's still pretty blurry at this level. So all we have to do, if we want to offset that, is just subtract some value from this before we clamp it. So if we add something like -1 or -1.5, actually just -1, yeah, and then clamp that. Now we can see that everything is basically clear at the top, clear at the surface, and then it blurs out as it goes deeper. And then if I turn this opacity down to 0, you can see also that we're not getting that black effect anymore because we, again, clamped the LOD level from 0 to 6. And if we go under the water, we still haven't fixed this, but this is a very easy, well, it is fixed, but it's always sampling basically the lowest LOD level because, again, since this is just sampling the skybox depth, we just have a massive, but the depth is just very large here, so it's always sampling LOD level 6. But what we can do is just take this front face bull to float conversion and just simply multiply before we clamp it and subtract, we can just multiply this subtraction value with this float conversion, then add -1. There. Now if we save that, this will always be, now as you can see, we're sampling the LOD level 0 when we're under the water, and then it works as usual when we're above the water. This. You could also clamp this if you didn't want like the LOD 0. You could clamp this to like a, maybe like to use LOD 1 or 2. If you didn't want it to be always clear, no matter like where you are on the. You could also, if you wanted, you could get a camera. This obviously has the position. So if we take that position and then split out the green channel, which is the Y, we can subtract. We can basically create like a delta that as we get lower beneath the water level, which is some Y value, then, you know, as that delta gets bigger, we can use that to sample the LOD level, so it'll blur out as we get deeper. Something you could do. But yeah, I think it looks, I like it as is. It always just sampling LOD level 0, and then you could, you know, take care of the actual underwater effects and just add like fog using a volume, like a, you know, like a sky fog volume. Just add another one down here. It'll take care of the water effects and all that. But yeah, I think that's everything I wanted to go over. If you have any, you know, tips or suggestions on how I might be able to improve this, please let me know. If there was something that was confusing to you, tell me. Oh, I will. So I'll enable the screen space reflections real quick as well. Take a look at that. So you can see this screen space reflection right there. Right here in the wave crest, or the edge of the wave, it's the sphere. So we have the reflections as well as the depth refraction. To enable, if you did want to enable the screen space reflections, you'll have to go to your, if you're using HDRP, you go to your HDRP global settings, and if we scroll down to this camera right here in the frame settings, and we go to, I believe it's in rendering, so you go to the camera lighting tab, and then we have screen space reflection right here, and then we want to check transparency as well. If we uncheck that, you can see that our screen space reflections are turning on and off for this material. So yeah, that should be everything. Guess I'll finish the housekeeping things here. Just again, group all this stuff into a category. I'll call this water parameters. Move that to the top to be there. And then group our opacity / refraction. This. And that should take care of everything. Yeah. One last thing you could think about as well is creating different quality levels. So if we take a we get like a material quality keyword and sample this. We can use that to control whether or not we, use this these calculations for the for clamping the screen space position, refraction and all that. We could use a material quality keyword to change if we actually dynamically calculate this fall off value, or if we require it as just a constant, begin to save some operations to optimize the shader a little bit. Just thinking about small things like this could help improve the performance of your shader if you needed to, or if you want to have like different quality levels. You could use this node right here. Yeah, we have the defaults and obviously all that, but I'm not going to implement that right now. But yeah, I suggest if you do, or I suggest you should if you really want to optimize things. But yeah, I think that's the end of the tutorial. I hope this helped you, or helped some of you. Maybe learn something that learn a technique that you might not have been familiar with. Like either for the foam or for the depth and the depth blurring. But let me know how it worked out, and I will catch you next time.